Welcome everybody. Today I'm going to talk to you guys about the different types of collisions that you might run into in the class. There are 4 categories, and it's important to remember the overall guiding rule for all 4 of these is the law of conservation of momentum. That holds for everything. Okay, so we say momentum is conserved for every type of collision or explosion. The mathematical way of writing that is the sum of all the momenta at the beginning must equal the sum of all the momenta near the end or at some other later time. If I wanted to be more specific, I could write it out like this. I could say the momentum of object A at time 1 plus the momentum of object B at time 1 equals the momentum of object A at time 2 plus the momentum of object B at time 2. Important to remember, though, that each one is a vector, and so it's not necessarily that A stays whatever value it has at the beginning and to the end, and B likewise stays from the beginning to the end as a constant. It does not work that way. Because they're vectors, they end up changing up their individual numbers, their individual quantities, but the sum total stays the same. Okay, that's it. Now let's go ahead and talk about it real quick. So the first type is the type that you are least likely to ever run into, and that's an ideal collision. And this ideal collision has the name elastic. Like rubber is elastic, right? It stretches, right? So that's what we know the word elastic means. But for collisions, we mean perfectly bouncing. And so objects perfectly bounce off each other. They don't lose any kinetic energy. Of course, momentum still holds, so that's not a big deal because we know that that's going to be true no matter what. But the big thing is that it doesn't lose any kinetic energy. It's ideal, as I've written here, and it's important to remember that the only time that we can ever really come into contact with these kinds of collisions, or at least approximate these kinds of collisions in the real world, is on the atomic or molecular level. We have ideal gases. And so if you remember from your chemistry class, one of the stipulations for an ideal gas was that it has that its particles have elastic collisions. You probably don't remember that because you probably didn't worry too much about it. But that's what was meant, was that no kinetic energy is lost. Don't forget, kinetic energy of particles is another way of saying temperature. And so as a result, when you have an ideal gas, you don't want to have to factor in any temperature loss due to the collision, because then that throws off your beautiful mathematics. And so it is what it is. There it is. We make some assumptions. Chemistry, it turns out chemistry teachers and chemists also make very similar kinds of assumptions to make the math easier, but it is what it is. Okay, more likely is for you to come into contact with an inelastic collision. And so during an inelastic collision, objects tend to stick together a little bit or deform a little bit. And as a result, kinetic energy is lost because of that deformation or the stickiness. So here's an example. Let's say I have a super ball. Now a super ball is super bouncy, right? And so we could say it must be elastic. But in reality, it's not, because it does lose some kinetic energy. It's not a lot, but it is some. If you let it bounce, it will, over time, bounce lower and lower and lower and lower and lower until finally it stops on the floor. Where did that energy go? Well, the kinetic energy that you had now all of a sudden has become thermal energy in the floor or in the super ball itself. So as a result, it does lose some kinetic energy. It's not a lot, but it is some. And so it's important to remember that it's an inelastic collision. What that looks like is this. So here you have a nice round shape as the super ball is falling towards the ground. And as it's bouncing back up, it has a nice round shape. But in between, when it contacts the ground, you should see that it kind of makes an oblong shape like this, kind of as an oval shape. And in the process, all of the little particles that are in the floor here experience a collision. So they get a little bit of a force acting on them, an impulse that pushes them down or to the side, whatever, in all sorts of random directions. And so as a result, this area right here the particles in there tend to bounce around more. And as we just said, particles that bounce around more have a higher temperature. That temperature must come from someplace, and of course that's the kinetic energy. And so we're going to find out as we get into the energy unit next that kinetic energy is at a maximum here, and over here kinetic energy is lower. because in the process we've lost something to thermal energy. So thermal energy is increased in the collision process right there. And that's because it is somewhat inelastic in its collision. Now, as you might imagine, the other objects, like cars, for example, have extremely inelastic collisions where they tend to stick to and to deform with the shapes that they hit. If you've ever seen a car hit a tree, you can see that the front end of the car has crumpled around the tree in such a way to absorb some of the kinetic energy. The whole point is to try to keep the car as safe as possible and the people inside as safe as possible. And so as a result, people have purposefully designed and engineered those cars to absorb kinetic energy. And as a result, even though the momentum of the system must stay, the total momentum must stay the same, as a result, the kinetic energy is lost. There are circumstances where you could imagine a perfectly inelastic collision, or at least getting really close to a perfectly inelastic collision. The one that I like to use is a ball of Play-Doh that's thrown at high speed towards the ground. And so you might imagine that when that ball of Play-Doh hits the ground, it's going to flatten out like so, like that, like a pancake. So it's totally deformed at that point, right? And so where did the energy come to deform it? Well, it must have come from the kinetic energy it had when it was thrown downward. There we go. There we go. So that energy must have come from someplace, and as a result, it comes from the kinetic energy. So we have kinetic energy up here, but that kinetic energy is lost in a big way when it deforms. So the object itself absorbs some of the energy, and energy is used to change the shape of the object. Some of the energy, of course, is heating up the floor, and some of the energy is heating up the Play-Doh itself, but in the process, most of the energy that's lost ends up causing the shape itself to change. Now again, the same thing applies here where the total momentum of the system must be zero, so it's important to remember that. I also drew a couple of train cars, and so if you wanted to imagine here a train car here that had a velocity going this way, and then another train car that had a much smaller velocity going this way, when they hit each other and hold on to each other, they become one object. And as a result, that one object will have the same momentum as the two cars did together. And so as a result, their momentum is going to look something like that, because this mass times this velocity is much greater than this mass times that velocity, assuming the masses are the same. And so as a result, the momentum ends up being that direction as when it's all one object. Last but not least, we have explosions, and there's a reason why I put explosions next to perfectly inelastic collisions, because perfectly inelastic collision is like the time forward. So the movie is running forward to show you how things come together to form one object. An explosion is when the time is running backward, so when one object becomes multiple objects. And so if we look at it here, let's say we have a ball that, I don't know, let's say it's a firework, right? And so you've lit the fuse on the firework. Maybe the fuse looks like this, right? There it is. It's lit and it's burning down, and then there's gunpowder inside, and that gunpowder causes the three pieces on the outside to explode outward. And initially, the momentum that you have here for the system is zero. So in the end, though, this piece is flying off in this direction, this piece is flying off in that direction, and this piece is flying off in that direction. So each one has its own momentum. But if you add up those three vectors, you find that the total system momentum is still zero. And so even though at the initial state, the whole thing is not moving, in the final state, everything is moving. It's just moving in such a way that the total momentum of the system must be zero. And so that's how really they analyze explosions to try to find out where the epicenter of the explosion was, is they take all of the shrapnel and try to trace it back using vectors. It's pretty cool to be able to do that kind of thing, and people get paid pretty well to be able to do it. So if you're thinking about a future job involving physics, there you go. All right, thanks for watching. If you have any questions, please let me know.